Hi, this video we're going to cover a very important concept called mass and energy conservation in open system. Okay. First of all, open system is something when you have mass and energy both transfer in and out of the system. So for example, you can thinking about turbines, like our water heater, for example, and then we might have nozzles, diffusers. Opposite to the open system, we have closed system. Closed system, which means only energy can go in and out. Only energy can go in and out. But the mass does not change inside, right? However, what we are talking about, this one here is open system. So we're gonna have mass comes in and also energy comes in and out. Okay. So in order to learn this concept, I would like to invite you to look at the PowerPoint. So first we look at this one, conservation of mass principle. Here they're using a tub. You have water coming into the tub. You also have some drainage leaving down the bottom. So if the mass comes in is 50 kilogram and there's drainage going out is 30, obviously how much mass increase in that tub will be 50 minus 30 give us 20. That's the change. Also here, it increase of the mass inside the tub. So that's the equation. Mass coming minus mass going out is going to be delta, change of the mass inside this control volume. And now, what we're going to do is we're going to divide this equation by time on both left side and right hand equation. So think about when we divide by time, mass over time, that will be our mass flow rate, right? That'd be, so mass flow rate coming minus mass flow rate out. So that's m dot coming minus m dot out. That's going to be the change of the mass inside the control volume divided by time. Okay, so that's going to be another equation. And why do we have sigma here and sigma in and sigma out? Because sometimes you might have not only just one inlet and one outlet. You might have multiple inlets. For example, you might have two inlets coming, so you're going to combine both of them. And you might have three outlets, so you will have combined both three outlets together to consider all the mass going out. So then we're going to come to another concept called a steady state or steady flow. Steady flow means the property here, for example, is mass. Inside this control volume does not change. Okay, so means the mass stays constant inside this container, control volume. Even there's mass flow rate coming and also mass flow rate coming out. So in that case, the delta here is going to be equal to 0 because mass is constant. So there's no change. Delta will be equal to 0. So this entire term will be equal to 0. If that's equal to 0, we obviously conclude mass flow rate coming in equals mass flow rate coming out. So that's going to be our mass conservation equation. Okay. And for example here, you have two inlets. So mass flow rate coming in will be 2 kilogram plus 3 kilogram per second. That would be 5 kilograms per second. And what would be the M3 dot, the mass flow rate out? That would be 5 kilogram per second. So in this situation, you will know that inside this control volume, the mass stays constant. That's a steady flow device. So that's our mass conservation. Now let's move on to energy conservation. Before we come to this entire new equation for energy, we have to learn some concept first. The first concept is flow work. Flow work is also called flow energy. It's work required to push some sort of mass in and out. Because we are looking at an open system. Open system will have mass come in and out, and also have energy coming in and out. So when this mass come in, and there's going to require work to push it in and out, so it's going to be pressure times volume. Okay, so pressure times volume. Pressure has a unit of like force over area, so that'd be Newton per meter square, and then times volume times meter cube. So you get Newton times meter, force times distance. That gives us the work unit, the energy unit. So this work, flow work, is going to be pressure times volume. Okay. Now let's thinking about if the fluid is not flowing, which means there's no mass coming, and what constitute of the energy? We'll have internal energy, small u. We'll have kinetic energy, half mv squared. And here you get rid of mass because we're looking at a specific energy divided by mass. Then you also have potential energy. Instead of mgh, you get rid of m, that'd be gh or gz. However, we are thinking about open system. There will be flow work used to push fluid in and out. That flow work is, we talked about earlier, is pressure times volume, P times small v, because here we're looking at specific volume again, divided by mass. So we're going to add this term to U and V squared over 2 plus GZ. That's going to be entire energy. Now, we're going to looking at this. What is U plus PV? Can we combine these first two terms? We learned about enthalpy. Enthalpy is H. H is U plus PV right here. So in that situation, we actually write down this is going to be H plus V squared over 2 plus GZ. Okay, now we can times mass to get the entire energy. How many kilojoule? Because earlier we were looking at a kilojoule per kilogram in those two equations. So now we times the mass. Okay. And often, if the kinetic energy and potential energy is negligible, all we have left in this equation will be just m times h. And again, we're going to divide this by time. So mass divided by time will give us mass flow rate. So it will be mass flow rate times h. All right, so we're about to get to energy conservation equation. We borrow the concept we learned about in mass conservation. We're talking about mass flow rate coming in minus mass flow rate out is equal to this mass change over time. And we made assumption that it's a steady flow device, which means the mass inside is constant. Here we make the same assumption, which means energy of the system stays constant. So in that case, there'll be no change of the energy. So dE over dt will be equal to 0. Then what does it give us? We get the similar results as mass conservation. Will be the energy conservation, energy coming in, energy flow rate coming in is equal to energy flow rate coming out. So E dot in is equal to E dot out. And we're going to expand this equation. We think about what contribute the energy coming. We could heat it up, right? We could have a candle burning underneath. That's a heat coming. Also, we can put work into it. We can compress a piston cylinder. That's work coming. Or, for example, we can have a resistor going through electrical resistance. That's electrical work coming. And also, because this is open device, open system. So we'll have this equation we're trying to derive earlier, mass flow rate times H plus kinetic energy plus GZ. as for each inlet added together, that's going to be equal to what's coming out. Coming out is pretty much a mirror image of what you have here. There's a heat coming out, you could have a system, there's a heat leaking out. You could be having work down by the system, work out of the system. For example, would be like a piston being expanded, being pushed up. Also, you have the mass flow rate to leave in the system. So then you have mass flow rate H plus half V squared plus GZ. So that is our big equation for our energy conservation. So knowing that now, I'm going to write down those two major equations we just investigated, and here we are. It's our quick summary. So for mass conservation, for open system, we will summation of inlet of mass flow rate equal to summation of all out mass flow rate out. Then for energy conservation, we'll have the same pattern. Energy flow rate coming of all the inlets is going to be equal to energy flow rate coming out of all the outlets. Then we actually expand this because energy could be in different form, could be in heat transfer, and also could be work coming into the system. Also, because it's an open system, you're going to have different inlet coming. So this is sigma. Then you have mass flow rate. Then first term is our enthalpy, which is combination of U plus PV, right? Then plus half V squared plus GZ. So that's all the inlet. So the right side will be exactly the same thing. You could have heat coming out of the system and work going out of the system, and potentially you have mass leaving out of the system. So it will be summation of all the outlets and mass flow rate and H plus half V squared plus GZ. So that's for entire energy conservation equation. Okay, so that's a very long equation, as you can see, but really it's not too complicated, right? Because if you know energy is made of, heat, work, and the flow work, then the left and the right side is pretty much the same. So knowing this, moving forward, in the next couple of the videos, we will be using mass conservation and energy conservation, and we are solving quite a few numbers of open system device. Just give you a heads up, we're going to be looking at turbine, nozzle diffuser, throttling device, heat exchanger, mixing chamber, all of that fun stuff. So, all right, I'll see you next time. Bye now.